This UCSD TV program is a presentation of University of California Television. Your support makes UCTV's programming possible. Contribute online at uctv.tv/support. Check out the YouTube original channel UCTV Prime at youtube.com/UCTV Prime. Subscribe today to get new programs every week.
Good evening and welcome to the Birch Aquarium at Scripps Institution of Oceanography. My name is Nigella Hilgarth and I am the Executive Director here at the Birch Aquarium. And this is the most recent in the Jeff B. Graham Perspectives on Ocean Science lecture series. And it's my great pleasure to introduce to you tonight's speaker, Dr. Frank Vernon. Dr. Frank Vernon obtained his BA in physics here at UC San Diego in earth science in 1977, and then his doctorate in earth sciences from UCSD in 1989. And he is presently a research seismologist at the Institute of Geophysics and Planetary Physics here at Scripps Institution of Oceanography at UC San Diego. And his current research interests are focused on developing real-time sensor networks in terrestrial and marine environments. And currently, he's the director of the U.S. Array Network Facility for the National Science Foundation, EarthScope MRE. And this network currently has over 400 seismic stations delivering real-time data here to UC San Diego, and then from here to redistributed to other multiple sites. And the most recent project that he is involved in is the Ocean Observatories Initiative, also with the National Science Foundation. And that started in September 2009, and he's the Deputy Director of the Cyber Infrastructure portion of that project, which really is, to put it very simply, is the glue that binds it all together and makes it interpretable. And so OOI is collecting real-time data and analyzing that data and modeling the ocean on multiple scales and enabling adaptive and interactive experimentation within the ocean. Very exciting project. And Dr. Vernon is also the principal investigator on the ANZA broadband and strong motion seismic network that he's operated since 1982, and that provides real-time seismic monitoring for here in Southern California. And so that is a really good lead into his presentation tonight. Is entitled Seismic Networks and Arrays, Observing Earthquakes from Near and Far. So please join with me in welcoming Dr. Vernon tonight.
Thank you, Nigella. Well, I was concerned when I first got here that we wouldn't be able to see the slides with the sunset being so late and we're moving off of onto daylight savings time, but fortunately I guess we'll be able to see most of this stuff. As Nigella says, I've been working here for essentially my whole career, and I'm spending doing seismic observations as one of my primary expertise. And today I'm going to talk to you about, not so much about the cyber infrastructure side and all those technology-oriented things, but more about the data that we observe, the data we see, and what types of ways of visualizing it and looking at it in new ways, and things we're starting to learn about the Earth based on these large-scale experiments. So the first primary project that we're talking about today is the EarthScope Project, and that's a project that's run by the National Science Foundation. It was a major research equipment program started in 2003. And there's basically three components of that. And there's Plate Boundary Observatory, which was run by a group called UNAVCO out of Boulder, Colorado. SAFOD, which is a San Andreas Fault Observatory at Depth, which was run by Stanford and the U.S. Geological Survey. And then US Array, which is the component which I'm involved with, which is an array of seismic sensors set up across the U.S. to image the crust and mantle structure underneath the North American continent. So the US array observatory components that we have are a transportable array of order 400 stations, which was at a 70-kilometer grid when we started. The reality is we're up to over 500 stations now, and you'll see how those are deployed in a minute. There's also a flexible array component, which is about 2,100 portable equipment that's checked out by principal investigators for very dedicated research experiments. There's a reference network of 100 permanent seismic stations, which are already deployed and would be left deployed in the long term. And then there's a magnetotelluric component looking at the conductivity structure below in the crust and upper mantle also. So this image gives you a map of the assets all used in US Array. Now many of these are temporary deployments. The triangles here are permanent stations. The red triangles and the black triangles are the transportable array and flexible array components, and the blue dots so that you can see over here are all GPS monitoring equipment, things like that. And so there's many different types of instrumentation deployed, but we're going to talk today about the seismological component of this. So as I said before, the reference network is about 100 permanent stations. It's a fixed fiducial network, basically giving us something to anchor all our measurements to. The transportable array, basically, we'll see just moves starts from the west coast and migrates us all the way to the east coast. And the flexible array, which is just a lot of very focused experiments, like something like you might want to look at what's going on at the Yellowstone hotspot or what's going on in the Cascadia subduction zone. So you put a bunch of experiments in there for 2 or 3 years and then get your data and pull it out. And say the magnetotelluric, which is the equivalent of the transportable array, working in the background. For the US array, the transportable array network, we basically have, here's what a field station looks like. This one is 345A and it looks like it's in Mississippi, and we have every single station, we have photographs of the installations, all run by solar panels, and they're all buried underground. Sensors are put this is in a sewer pipe, and it's dropped about 2 meters below the surface, a concrete pad, broadband seismic sensor, sometimes a strong motion sensor, data acquisition system, and then currently we're also putting infrasound on these systems and I'll go into that a bit later. All locally powered by solar, and then data sent either by cell phone or some other satellite communication, depending on what it is. But we receive all the data here in real time and process it all in real time. This is an animation of how the stations are actually deployed. The red stations are the US array, the blue stations are contributed by Caltech, yellow by UCSD, and there were some green ones from Berkeley up there. And so you can see how we actually are migrating across the country. This started in 2004, and we're migrating out to current date. And you'll see as of now, the end of last month, we finally hit the Atlantic Ocean out here. And you will see that's how these stations move. Each station's in place for about 2 years. They migrate across the country, and it's about a 70-kilometer station spacing, so we can get an image of everything going on. In the long term, after we roll, you can guess, as you say, look again, as we roll across the country here, you can see that we're going to come to a problem over here. We're going to get to that Atlantic Ocean, and these things are not OBSs. So I'm sorry, I mean, I know this is an ocean perspective thing, but I'm talking all about land stuff. Every measurement I make's on land in this particular talk here. So you can see where we're going to roll across. Here we are again, coming across. But next year, end of the year, we're going to be right about here, and by end of 2013, we're going to be out in Maine. Got to go somewhere. So instead of going swimming, we'll come back over here, and we're planning to go to Alaska, which has its own set of issues deploying instruments. I mean, where we use cell phones and have nice power systems and the sun's up all year round, you get above here, we have a whole winter where you can't get sunlight, and we have no cell phone communications, and this whole region up here, which is bigger than a good number of states, doesn't even have a single seismic station in it. So we have our challenges coming to us in the next 5-year part of this particular program. So I'm looking at this problem the other way around now. This is a little bit washed out, and apologize for that, but you can sort of get a sense that here's the North American continent on here. You can use your good imagination. Well, anchor ourselves. Here's the San Andreas Fault. Here's the Aleutian Arc. Here's going out into Kurils, into Japan, into the Marianas, and looking around through Indonesia where the Banda Aceh earthquake was, down over here in New Zealand and Tonga, and so forth. So you can see these are all the earthquakes that we have used to record in US array since 2004. And these are all magnitude 4.5 or above, and we use them to illuminate the crustal structure and a mantle structure underneath the North American continent here in a tomographic image. Same type technology, same type of concept that you'd use in medical tomography. So before we started US array, we started out with, this is the kind of our knowledge base, and here's California, here's the state here, Nevada. You can see this is the best resolution we could get, and every one of these images was a different type of tomography done by different researchers, but this 2001 by Kenny Duker, Mike Richwaller 2002, Montelli in 2004, and Steve Grand in 2002. So you can see we don't have a lot of resolution here. Things are kind of like very hazy, very kind of a wash through here, and then like these long wavelength signals here. And this one is probably the best of them, but it's still not all that good. I mean, you kind of see some features in here. That might be Yellowstone and hot spot up there, and the deep valleys here. Oh, there's a Sierra Nevada, but not particularly high resolution. So by 2008, we started doing an annual set of tomographic images so we can watch the progression as we go across the country. And so you can see a much higher resolution. Well, this is 4 years into the program, and you start seeing that there's much more detail on the Yellowstone hotspot. You can see images of going down to 200 kilometers depth. You see other structures that go in various areas here. But then you jump to 2009, and all of a sudden you see a much higher resolution. And basically this is just the ability to acquire a lot more data. We're basically bringing data in, we're continuously recording, we get it all the time, and each earthquake comes in and illuminates the whole array. And so as one earthquake comes from down near Tonga and illuminates this way, comes from Japan and illuminates this way, comes from Mid-Atlantic Ridge and illuminates this way, we start being able to construct an image of how the structure of the Earth appears underneath us. So this is where we were in 2009. You're starting to see, well, there's still, and you can see very clearly here that we get pretty high resolution where the sensors were in 2009. And then you can look out on the eastern part of the country, and it's still just as sparse. So, but then we can move on to 2010. You start seeing much higher resolution back up in this area as we migrate further and further eastward. And this is the most recent publication. You start seeing much more coverage here in this part of the country, and we're moving out, getting good imagery out, at least onto the Great Plains. We're basically through the Rocky Mountains at this point. And we will continue this type of work all the way through. But you can look even for the last, from 2009, 2010, you can see up in here, 2012, there's just quite a bit more structure that you're seeing. Now these are all plan views, and so we're talking about 100 kilometer depth, 200 kilometer depth, 300, 400, 500, 600. So we're looking all the way down basically to the transition zone in the mantle. Now we can look at it another way. You can take cross sections across, and so this one, we'll look at this from the Burdick et al. 2008 paper, and we're looking at cross sections basically taken across the degrees of longitude here, 45 north, 40 and 35, cutting across, and we're looking across here in the state of Washington, where we know there's a subduction zone in through here. Then we come across to Northern California, and then we'll look across in Southern California. And you can start seeing that quite a bit of imagery. Even in 2008, when we first started, you start seeing these were the best images of the Farallon subduction zone that have been made up to that point in time. And you can start seeing this D to D prime image here is basically bullseyed right on Yellowstone. So this is an image of the velocity structure, indicating there's quite a bit of velocity change underneath the hot spot there at Yellowstone, going down to a couple hundred kilometers in this particular image. But now we look in 2012, we'll look at a little bit longer arcs. The arcs are somewhat different. I'm sorry that they're not exactly the same, but you still get the same idea. And now you start seeing, like, here's the Farallon subduction zone. You can see it transitioning all the way down, maybe a step off here, this part underneath Utah, and this part of the Wyoming border right up in here. But you see a lot more structure of what's being resolved across the U.S. And we're basically now, we have a very good image basically somewhere out into the Great Plains areas. And now the question is, what are we going to find when we get out here? I mean, everyone said, well, you can't do anything. When you go out to Kansas, you'll never see it. There's nothing interesting out there. Well, I'm willing to bet you, if we can get this kind of resolution and get that kind of resolution, what's going on over here, we're going to find something interesting. We have no idea what is there right now. So there's a lot of very interesting understanding of what the structure of the Earth is and how it's put together. So another function of this particular program is, I mean, you can think of it as we can look at it as a seismic array where we record all these things from teleseismic distances. We can make these great images. We can start getting a better understanding of the Earth's crust. But there's another attribute. I mean, think about this. We're laying out a grid of seismometers on a 70-kilometer spacing, basically covering the whole U.S. We also allows us to get a better view of what's happening in the local regions. Now, for some strange reason, that almost all the permanent seismic networks are in California, state of Washington, and Alaska, and Hawaii. But, you know, it seems to be every place you put out a seismic network, there's earthquakes. Or is it the other way around? I'm not quite sure which here, you know. But this is these are the seismic events observed through all the various regional and national networks we have in the U.S. And you can see, as you know, all the things we expect to see: San Andreas Fault, all our activity here in Southern California, the backside of the Sierras, the Mendocino Fracture Zone going offshore, and the Cascadia area, Cascadia Subduction Zone, the earthquake belts up in the Basin and Range up in Idaho and Montana. Fairly things. There's some oddities here in Oklahoma and a few other places here that have occurred in the past few years, which you've heard about on the news, I'm sure. But then we look at these are the earthquakes and events that have been only seen through US Array. They were not seen through the background networks. And as we move across the country, we get a much higher resolution coverage. So you see there's a lot more events occurring in these regions. It's interesting enough, we see a lot more events offshore that were not seen in the previous map. We see a lot of events here, but those turn out to be a set of mines and quarries that are up in British Columbia. We also get a lot of events back in Wyoming, which also happen to be a lot of mines and things. But a significant number of these events are actual earthquakes that were not observed through other systems in place, because we tend to focus where the people are and where the primary earthquake faults are. So this gives you an idea. We're getting a kind of a 2-year snapshot at a time of what the background seismicity in the continental US is, much higher resolution than was ever seen before. And then when you merge the two sets together, you say, okay, well, that's what we get with just US Array, this is what we get with everybody, and so that's kind of the best view that we've been seeing. And kind of the interesting thing is we've been seeing these earthquakes in southern Colorado, which had an interesting earthquake storm. We've had this sequence of events in Oklahoma. We've had a sequence of events in Arkansas. And we've also had a significant number of earthquakes down in southern Texas, which is, who knows? You know, this is not things I expected to see. I expected that section of the country to be pretty quiet from a seismicity perspective when we moved out there. But and then we also have the Virginia earthquake, which we actually recorded out here, but you know, it's fairly big earthquakes, and we didn't have all our stations aren't that far east yet. So we're going to jump now to kind of one of the events of interest, and we're at the first anniversary of the Tohoku Japanese earthquake, the one that caused the major tsunami and the events that are associated with it. And so I'm going to give you sort of a view on how we observe this with US Array and some of the interesting results that we are seeing and how the whole Earth responds to this sort of major scale event. As we all know, it's a magnitude 9 earthquake. It's a huge, huge event. This is basically, these contours are the areas of the rupture as done by the rupture model by Chuck Amon and Thornley and Hiro Kanamori. And you can see the red dot here is the main shock. That was where its epicenter was, but the biggest slip appears to have occurred in this particular region. The rest of the red dots are aftershocks of the main earthquake. There was a foreshock about magnitude 7, low 7s that occurred like 2 days before, and that's the green dots here, and the green dots are those aftershocks. But you can see here's the major subduction zone. Here's where the Earth moved. This is where we have these huge motions in the seafloor causing the major tsunamis that hit Japan and this region all the way on up to here and all the way on down, as well as propagating out to here. And those of us who got cast with the news had to go down and see if we could see it come in here at Scripps Beach on that day. So fortunately, we didn't see much. So this is a distribution of the aftershocks for that whole sequence, again done by Chuck Amon. I'm going to give you an animation, but this is the total number of aftershocks. You can get a sense of how fast things happen and how, in one sense they happen really quickly, in another sense they happen in bursts. They're just impulses happening all the time. So this is where the main earthquake occurs, and here's the animation and basically several hour time slices, and they will fade away after 1 week of data here. And we're going to show you about 1 month of this animation here. So you can get the sense of how big this particular earthquake was, these major aftershocks occurring constantly. And this is clearly something we don't want to see in our backyard, but unfortunately we have the opportunity up in Oregon, Washington, and Vancouver Island and British Columbia with the Cascadia subduction zone, which is of similar size and could have a similar earthquake to this one at some point. And we know that last one was in 1700, so over 300 years ago. So, but when an earthquake happens, I mean, we have the issues of the local artifacts, the things that have occurred during this particular event. And we know the tremendous amount of destruction, the tsunami, the early warning systems that worked, the things that failed. I mean, we've seen this all on the news. They've had this really interesting show on Nova the other day, which was also looking at the anniversary. But we can also look at this. I mean, here's how we saw it from sitting in the US. And so on the day of that earthquake, this was the distribution of seismic stations in US array. So where the main part of the array is sitting over here in the center of the country, just basically west of the Mississippi. We're still, Caltech's still contributing data and looking at the array, so as part of the array. And then we also reoccupied this, what we call a Cascadia project, where we reinstall a bunch of stations to monitor the subduction zone here, which is basically the equivalent of what's going on over here. So you look at a single station, traditional seismology, here's a seismogram, here we go. Okay, we've got a P wave, got an S wave, got a surface wave here, got another surface wave, and here's what it looks like, and that's, a trained seismologist is going to go to town looking at these things, trying to interpret it, get more understanding of how the Earth works out of it. But actually, we had 400 stations, and so I can't show 400 stations on here because each little pixel would be about like this, and this whole thing would be yellow, and you wouldn't understand a thing, and neither would I. So we've just basically organized this display that the closest station was up top, and every 8th station in distance further away is moving down the plot. So you can see the P waves, and you can see the first arrivals here. It gets later was farther away. We have other body wave phases coming in here. We have surface waves coming in slower and slower as you get further and further away, and we use these slower velocities in there. Another way you could have looked at it is what you do this record section plot. And so you have the P waves all lined up perfectly vertical, and then the next phase is coming in here. You can see it very clearly. And here's what the Rayleigh waves, the surface waves that come in along on the vertical components here. And you can see that here's the closest station. The closest station for the US array was about 65 degrees. 65 degrees is about 6,600 kilometers or so order of 5,000 miles from the original, from the source sort of thing. We get out to 95 degrees is the furthest stations away that are in the North American continent part of US array. So you see the surface waves going out, and then you notice this. Oh yeah, they're coming back again, the other direction. These are phases that have gone around the world. You see, if you have a globe such as this, you have an earthquake here, the first one comes over to US array, the second round comes back the other way. So the whole Earth is ringing. These phases are propagating back and forth. And then it comes back around, wraps back again, and if you look really hard, you can see in here, and if I played more filtering games and did something, a different display, you would see this wrap around 10, 20 times. It's pretty astounding, large earthquakes. So we're going to look at this. Okay, so now here's the source, and basically here's an approximation of the ray path, and it's going to come in from the northwest into US array. You're going to see this data here, and we're going to look at some animations. And so these animations, you'll see red is up and blue is down. You can see the seismic waves propagating across, coming down from Japan, as you would expect. These are sped up quite a bit in real time, the actual number of seconds since the original thing. Here's the Rayleigh wave here. And this is just looking up and down. This just gives you a sense of the type of thing that we're observing here. And pretty soon you start seeing something interesting. You start seeing some changes in character. See things like going back up the other way now? You see things like that? Those are phases that bounce off the far side of the Earth and come back at you the opposite direction.
What's the magnitude?
Well, the magnitude of this is about 3 millimeters. This is one particular station here, so you can see the amplitude is about 3 millimeters of motion. And these are very low pass filtered, so you're looking at about 100 seconds or beyond. And so in here, so this is where R1 came across this way. That's the Rayleigh wave coming across. And now we're looking at R2, and you see it coming back up from the other side, just like the other view looked at it. But this animation gives you a much better sense of what's going on in how the Earth is interacting. So now we're going to have a bit more fun. So we don't just measure through one component of motion. We don't measure just up and down. We measure the 3 components of motion. So we go up and down, we go north and south, and we go east and west. And so once you do that, you can do exactly the same thing, except we're going to put little sticks in here, which gives you the sense of horizontal motion also. So the red and the blue gives you the up and down, which is the same as before. But now when you start seeing the shear waves come across, so you can see pretty much motion sweeping across there. See, okay, I don't know how many of you had your seismology course, but we'll have seismology 101 right here. The wave propagates this way, shear waves move in perpendicular directions to the direction of propagation. How clear can you make this?
Would you see that across the whole western United States?
If you had sensors if we left the grid in, which we had, yes. I'm sorry? The question was, would you seen the same effect if we had left all the sensors back in here? And this type of phenomena you see. So you see the large-scale structures, and that's actually a point I was going to point into. You can see in Southern California we have a tight grid of sensors, so you can see some of it, but it's not really big enough to see the large-scale phenomena here. The other thing is when we continue on in the animation, look in here. Imagine if you didn't have this and you didn't have this, what you could interpret out of it. And you'll find very quickly that it's not very simple. So here we go, watching through there. And now we get to, okay, there's 2 types of surface waves that propagate along the surface of the Earth. And one's a horizontally polarized wave, which is called a love wave, and that's this phase that's right here. And you can see, again, it's perpendicular to the direction of propagation, which is going kind of northwest to southeast in this part here. Okay, so you'll see we're back here in the love waves, right where we left off before. And here what you can see is that this particular station is this yellow mark right here. So right here we're between what's called the love waves, which are travel a little faster than the Rayleigh waves. But what's kind of cool, that's on the front end, is that the love waves are horizontally polarized here, right? But look up the back end of the country. Look what's trailing. The Rayleigh waves, which are polarized along the direction of propagation, are all up here. So you can see it trailing, and the direction of motion at each station has changed across the country. And you can trap this and show this quite graphically. And you see these various phases sweep through, and I mean, it's just, imagine, just think about the whole Earth resonating and how it might move back and forth. And I can't quite figure out whether I'm literally looking at kelp watching in the ocean or something or what here. So, and you see things come back up. But this is the ground moving, and it's millimeters. You can't quite feel it. It's too slow for you to feel, but it's, yeah, but you're still talking fairly significant motion here. And we're only at 2 hours after the earthquake, and it's still doing all this. Yep.
Sorry, there's one sensor that seems to be has been going moving before the earthquake went off, and then it's doing something different. I don't know whether was that because there was some other event that was going on there.
More than likely, it may have been some issue with that particular. The question was there's an anomalous sensor in response inside these 500 stations, and most likely that's some problem on that individual sensor as opposed to the something anomalous at that particular station. But it's a coupling of geology, it's a coupling of what the site response is, it's a coupling of what the earthquake actually is doing. All right, so we had enough fun with that one. So, but wait a minute, let's turn the problem around backwards. Now we're sitting out here looking at all stations. Let's see what we can learn, what we can image from this side, back projecting back to the source. And this is the work done by the Kieser and Ishii at Harvard. And there's this imaging the earthquake as it occurs and the areas of rupture, the primary energy sources. This is the epicenter. These are the primary energy sources that they could identify through the time sequence of the earthquake. So the three red areas are the dominant areas of motion. These yellow areas are now considered aftershocks because it's after the main rupture there. And you can see how the area sort of fills in over a function of time. And this is the coast of Japan, and here's the subduction zone. So we're taking US ray and projecting all the way back over to the source area. And so here's, again, so the red areas are the three primary energy sources of the main shock. The yellows are the first sets of aftershocks that are observing, and the yellow dots are other aftershocks that are observed. But it gives you an idea how the same data set can be used in multiple different ways to get a better understanding of both the source region as well as the areas that you're actually making the recordings in. So this one is, I'm going to show you evidence of an earthquake which is much less in size and didn't hit the news as much, was in the US, but not many people lived out near Wells, Nevada. But the interesting thing here is you can play a little game with it. So here's the earthquake when it occurred. Here's the array when we set, it's like we almost predicted this one, right? We set the array here and the earthquake occurred right in the middle of it. What more do you want? Might as well go home. But the other little entertainment factor of this one is like, okay, you have this earthquake, you can see it in the middle. Well, what did we just talk about? We showed how on big earthquakes, signals go all the way out, they go around the world, then come back the other way, and go around the world, and things like that, right? Well, think about this. We have an opportunity here where the earthquake occurs, signals go all the way around the world, come all the way back and refocus back at the same place where it started, and we can actually image this. So if it were a perfectly homogeneous world, we would be sitting there and the energy would go all the way out and it would focus all the way back and it'd be exactly the same thing. So let's see what really happened. So here's the signal going out, propagating away. Oh, and here it is coming back at you. And so when you hit the big signal here, and this should refocus right about there if it were a perfect world. I guess we don't quite live in a perfect world, do we? Comes close. So that's just basically how signals propagate all the way around the world, and then they re-interact and they phase together and basically sum and difference back into the region which they source. And they would continue doing that if it were a big earthquake. We could do that for several different orbits of the Earth. But this is just kind of an amazing example that we exactly put it in the center of the array. So one thing else I wanted to talk about today was that we, based on some observations early on, back when the array was centered on the very west coast of the US and states of Oregon, Washington, and California, we had a meteorite hit overhead. And it created all these signals. And we have this, just like we're looking at the Earth, we're looking at signals propagate up through the Earth. We had the opposite. We had stuff propagating through the atmosphere, and we could propagate things all the way across. So as a result of that, Mike Hedlund and myself wrote a proposal saying, gee, it might be kind of interesting to add barometric sensors and infrasound sensors onto our experiment, because basically we already have the problem solved of permitting, installation, construction, data acquisition, data telemetry, archiving, all that's done. All we have to do is add on a couple more sensors. Not that hard, particularly with all the other hard work done. So this gives basically three types of sensors with three different frequency responses, and pretty much the ones we care about the most are the Cetra barometer, which goes down to basically DC, or basically measures atmospheric pressure. We'll see this. And then the infrasound sensors, which are basically microphones that come up almost in the audible range. We only go up to 20 hertz, so my hearing's not good enough to get down there, but if we took it up to 100 hertz or to a couple hundred hertz would be good. So to cover the whole observational band. So you can see here's the image. These things are ones with the MEMS sensors only, which we just started with. And then when they start putting black symbols in here, right about there, those have the full sensor suite, and that's where we're working right now. So basically all the West Coast has these, and the center section of the country here, and pretty much starting in 2011 is where we started putting in a lot of the barometric and infrasound sensors. So this is an image of the atmospheric pressure, and this is fairly typical. The only thing that's unusual about it is, again, we looked at a very tight grid. We have a 70-kilometer station spacing, so it's much denser than any of the meteorological networks, and we sample at a much higher rate because we sample at 1 sample per second and 40 samples per second. But here we're basically looking at the big weather systems moving across last April, and every red square here is where a known tornado happened. This is that main tornado sweep comes up in a second here. So you see it propagating across the country. But we were trying to look at what the pressure sensors are. You see the low pressure in here, working across, and we did have some fairly close passes to some of our stations. I'll show you an example of that kind of data. But let's look at it from a different perspective. Let's just filter these data, and we can say, okay, instead of looking at the big overall DC, big weather pattern, front coming across, right? We're going to filter this data. We're going to filter it in a band of 2 to 6 hours, so it kind of narrows the response that we can see, but it also might give us some more insight. So you see these very interesting signals, and you'll watch these things propagate up and down the US from various different sources. So this is very pretty new stuff, so we haven't sorted all of this out. So you get to see us in action. We get excited about something that we haven't seen before, and we don't quite understand all that we see yet. See these things propagating from the west there. Clearly something happened out there. Something propagated there, up and down. Then right about here, we see the biggest signal that we observed. Right there. Look at how this signal here propagates all the way up the country and propagates down. Something very large there occurred in the atmosphere, which I haven't been able to pin down yet, but one of the projects for the next few months is to sort out this particular signal as it propagates across there. So this is a snapshot of basically by the same time I stopped it before. You see the signals and two different time windows here. This is on the April 27th at 3 o'clock GMT and at 7 o'clock GMT. So you can see these signals here, starting here, propagating northward, so it's much more northern in here. The interesting thing from a seismological perspective is that you can take this signal here, and you can look in there, and then you can see that the barometric pressure is the black sensor. Well, if you've got really good eyes and you can see this, there's actually a red signal which is also right there, and that is actually showing up in the seismic data. So we see this same signal which is propagating from the atmosphere into the Earth and being able to be resolved to a correlation coefficient of 0.992, which is basically unity. I mean, it's the same signal. And so we see this type of thing at the various seismic stations that are also propagating in from the barometer. And that's actually how we argued to get the funding for the barometric thing, is to try and be able to remove and understand the noise signal caused from the atmospheric signals that's not coming from the seismic from the Earth. But we're going to also turn it around the other way, go exploring and figure out, okay, what are the things about the atmosphere we didn't know before, and what are the features that we can understand. So if you look across the country, we can make a record section, sort of like we did before, looking at the earthquake signal, but now we're looking at signals of this, what they call a gravity wave in the atmosphere, propagating up from south to north. And instead of seismic velocities where things move across the country in order of minutes, we're looking at order of hours that it takes for those things to propagate south to north. It's actually a pretty fascinating signal. And then you can look in this is just the barometric pressure signal that you find here, and this is the best orientation of the rotation of the horizontal seismic sensors to match. And then basically every one of these is in the well above 0.9% correlation, which is just, I mean, it's just an astonishing actual observation that it can be tied that close. But then we're out there, we also had some other weather phenomena roll by last year, and we are currently doing the same thing this year. This was a tornado that went through Jackson, Mississippi on the 15th of April last year. This is an actual image of the particular tornado. And since we got barometric pressure in there, you can start seeing some pretty interesting signals. So what I'm showing you here are images. We have the time series showing from the infrasound sensors and from the MEMS sensors. We have a radar image at this particular snapshot in time of the thunderstorm front as it moves across Jackson, Mississippi. We have a Doppler image here with this, and this is a characteristic hook which is characteristic of tornadoes. This is the seismic station 245A right out in front of it, and this line here corresponds to this time snapshot. And this basically is another image of the debris field, basically, so it gives you another indicator that there's a tornado coming at you. So now here we are just before this big rise in pressure. So you can see that we're still not quite there yet, and something's going to start happening. And if you actually look at that, that's a 5 millibar jump in order of a minute. I mean, things are really, really going dynamic in the atmosphere right there. And then just as we cross, we hit this high frequency, this very high peak. We drop down and we go into this very high frequency signal. And so we see this kind of characteristic. This is probably, we have about 10 that we've started analyzing so far, and this is probably a topic of a whole nother conversation, but this is a very interesting piece of work where we're starting to, when you get out and put sensors in a way that you don't necessarily expect to know what you're going to see, serendipitously, you start finding a lot of interesting signals that will lead you in other directions that you would not have thought you would have been exploring 2 years ago. So getting back to the seismology side, I'm going to bring you back into Southern California. How many of you here felt the Easter earthquake in 2010? There's a couple. I know I did. It's one of those things you wake and you're upstairs in the house, you kind of go, I really don't want to go to work on Sunday afternoon, but I guess it's my job. So this is this is how I felt, right? This is the nearest seismometer we had on the U.S. array, and it clipped the daylight out of it. Everything's flat lined up here. I felt the same way. So here's the signal coming out, the same animation as before, type animation before. You can see the signal's propagating away from U.S. array. One of the things about this particular animation is that the signal's so big and we're so close to a magnitude 7 earthquake that the rest of it is a little bit less spectacular, so I have to manipulate it a bit more to make it show some of the back wrapping phases of it, but that wasn't the point right now. So what happens when the Earth has an earthquake like this? Well, the earthquake occurred on the far side of this mountain ridge. All that wave just smacked the ground and knocked all the dust off of it. Rather spectacular image. I wish I'd have been these guys instead of sitting at home. And then with the aftermath of this is the road just below the border in Mexico where the fault crossed there and damaged the road quite severely. And for those of us who have to report to the office and start talking to the news media for the next 48 hours straight, these are the types of things you start looking at. And so these are one of the main displays that we have in our office. We have a bunch of seismograms coming in. This is not from the US array experiment, but this is from our local network that operates here. And you see lots and lots and lots and lots and lots and lots of aftershocks. These are all things that are automatically detected through the real-time processing systems. This is a 24-hour image. Biggest stuff happens up front, but it still goes on and on and on and on. For 24 hours, you're just kind of going, and my analysts and people who analyze data are going crazy at this point in time. They want to find a new profession. But 10 days later, you sort of get down to a little bit more sane mode. This is still much higher than what you would see today. I mean, I went and looked this afternoon. It's like, there's almost no events in here, but but you can still see, just like we saw in Japan on the aftershock sequence and from the Tohoku earthquake, you saw right away there's this massive influx of aftershocks occurring, and then as they taper off with time and delay and decay away, and so at some point in time they basically phase off into background seismicity. Now in a magnitude 7 earthquake, I mean, this takes months. And magnitude 9 is going to take over a year before we get back to something which they were considered what they were back to background. And now another question that we've looked at is kind of interesting: how soon can you measure an aftershock? And you can see that the ground here is shaking very, very hard, and it's like everything's saturated. Well, part of it's just reverberations bouncing around all the ground underneath us and things like that. And so is it stuff coming from the source? Is it coming from just the scattering that we're seeing, everything bouncing back off the mountains and under the ground there? But you can clearly see that there are aftershocks occurring fairly soon, but they don't start immediately. You can actually look inside there and fairly closely determine that there's not an immediate set of earthquakes happening right away. And so you can see that here's one here, here's one here, here's one coming in a bit later. So it's an interesting study in its own right, and we have some seismologists here who are working that particular problem. So we're getting towards the end here. I wanted to show you basically the same types of things I've showed you animations from real data, things, but you can also take those animations, or not the animation, but the raw data, and use that as constraints on building models for how the rupture actually occurred. So for this 7.2, the one that we felt here, this is an animation of that particular earthquake rupture, and you can see it. It was done up at the San Diego Supercomputer Center. You can see the signals propagating south to north and propagating out across the Salton Sea. Oh yeah, it's time to go to work. Yep, time San Diego there. And then up to Palm Springs and into Pasadena. So this is the type of capability that we're developing by integrating the sets of data with the models together, things like that, and getting a better understanding of how the Earth works in our area. One of the other things that, which is kind of, which I am personally concerned about, is that we also are concerned about possibilities of major earthquakes here on the southern San Andreas. Oh yeah, the San Jacinto runs right through here. That's only 100 kilometers away from us where we sit right now, and the Ulster Fault. So we do other types of things that we're concerned about whether or not there might be additional stressors on these particular faults. As it turned out, there was a magnitude 5 event up in here several months later, another 4 on the southern San Jacinto Fault, and these are in areas which one of my other experiments, which Nigella mentioned, is monitoring the San Jacinto Fault Zone. And so, independent of this earthquake, before we ever did this, we submitted a proposal to go put a densification of seismic instrumentation on the San Jacinto Fault. And so it's basically breaks it up into multiple segments. San Bernardino Valley, which goes all the way up into Lytle Creek on Cajon Pass. Those of you who drive up Interstate 15, it's right there. It goes over the mountains, you go up onto the Mojave Desert there. You talk about Hemet, there's the main section of the fault here, and then the Cayuga Creek Fault and Borrego Mountain, Superstition Hills, things like that. But we're in the process of putting a dense set of seismic sensors on there to monitor very precisely the motions associated with the fault and how seismic signals, just like I showed you on a broad scale from using US Array, we're using the same type techniques to measure very small scale features as signals propagate up and down this particular fault. So this experiment is just going out right now. I hate to say it, but we're getting really good at forcing weather systems here. I had a helicopter deployment scheduled 2 weeks ago, and that was the first snowstorm up in the mountains and we couldn't get in. We are scheduled to go in on Sunday, and if you look at the current weather report, it's supposed to be 3 to 5 inches of rain up in the mountains, snow level down to 2,000 feet, so we may have trouble next week too. So maybe I should stop trying to schedule this stuff until later in the year. But anyway, so we are doing a lot of active research. This is, say, topics that we can cover on another conversation. And I want to leave you with one of the primary local monitoring websites is http://eqinfo.ucsd.edu, and this gives you a snapshot view of what we see at any given time on a real-time basis here. And with that, I will be ready for questions if I remember to repeat them. So you're asking what I would recommend to the president about, you're talking about a current operating nuclear station, about whether you put...
We know,
well,
being brought up to certain specifications, but on future, they're looking at power, doing away with coal and possibility of nuclear power.
Okay, so looking at possibly putting a future nuclear power plant inside the U.S., I would certainly do a very careful study. We have a pretty good idea where the major seismic systems are. You would want to make sure that you are well away from any of the hazards that are out there. And
right.
So, I mean,
in 8 years, I'm amazed what they've accomplished.
And we have, I mean, there's more things that we're learning, right? I mean, look at Virginia, where they had a place where they didn't expect an earthquake to occur, and that occurred within tens of kilometers of a significant nuclear reactor, right? So, I mean, you can't say that any place is completely devoid of earthquake potential in the U.S. There are places that have much lower probabilities than others. So you'd want to look at that pretty closely and make sure you have the proper safety and security things in place. I mean, even in Japan, I mean, it's clear that the seismic shutdown worked perfectly. I mean, you just have to make sure you understand and assess all the potential hazards, because where they got what the biggest problem happened to be the tsunami, which was bigger than they expected. So
Well, I guess I'm saying, are you a little scared?
I'm scared of lots of things, but I think that's a thing that could be. I mean, I'm a Southern California born and raised, right? So I grew up under earthquakes. I'm not that scared of them. I've been in a significant number of them. I would definitely not want to be having building plants right next to faults and things like that. I want to push them to someplace where there's more stable areas, so much further inland. Yes?
Question, getting back to your early slides, the big one that came around and reflected it and back again.
Yep.
Does the return follow the same path?
Well, if it were as I said, the question is whether the seismic signals that propagate out around the Earth and come back again, do they follow the same path as they go round and round? If it were a perfectly homogeneous Earth, the answer would be yes. But it's not. We showed I showed those tomographic images where you see velocity contrast, so things will bend around and move back and forth. If it were a perfect return signal, that image at Wells wouldn't have that kind of modeled look at its highest amplitude. It would have actually peaked, and you would have seen it come back together and rise up at that one place. So what you're seeing there is just a manifestation of the way that the whole Earth is constructed, and it's close to a sphere, and it's close to fairly homogeneous, but it's not quite. And you see that. That's the actual what you see there. It's in the mantle. Every structure you can see. Jules?
So, talking about energy, one of the hot topics this day is fracking. And there's been some speculation. First, we were worried about benzene, now we feel like it's okay. And there's been some speculation that fracking actually increases seismic activity. So what I'm curious to know if there's some interest in vigilance on the part of companies that are harvesting natural gas to either verify or refute the theory that fracking increases seismic activity.
There is a correlation that people are observing, but it appears to be not so much associated with the fracking as the issue of the re-injection of the fluids, which tends to be deeper. The earthquakes tend to be a little bit deeper than where the fracking occurs in both in Oklahoma and other places. So there's a correlation there. We don't understand the physics of it yet and know whether there's actually causality in all of this yet. But there is certainly.
Is it a hazard?
I'm sorry?
Is it a hazard?
It could be a hazard if you triggered something on the magnitude 4 or 5 scale and you're very close by. On a large scale, on a major tectonic thing, I would expect no.
So, thank you very much, Frank. I'm sure you'd be glad to stay and answer a few questions afterward. Thank you all for coming.